Hey, okay, cool. So we're gonna keep talking about hypothesis testing. Okay, it's what we're gonna do for the rest of the semester for the class. This is the big topic, and we're gonna delve more deeply into what we're talking about. Cool. So let me change to window mode. I'll try not to do too much. Okay, so this is in the book. Oh crap. I need to zoom in. In the book, 6.1. Okay, so what we're going to learn is that there are different hypothesis tests. And we're going to talk about how they are different, but they're actually quite the same. Okay, so you're going to see that like these different hypothesis tests, they're hypothesis tests about different things, but they're basically the same process. So what remains the same is the process. Okay, so let's talk about like how this is going to go down to remind people. Okay, so remember that you have the sample and you have your population. Okay. The thing that you're making a guess about in the population is called the parameter. And then you have whatever is in the sample is the statistic. And we have a special name for when you use the statistic to estimate the parameter. What is that called when you use what you saw in your sample as a guess for the parameter? I guess instead of statistic, we also sometimes call it the point estimate. You could use those interchangeably. Yeah, inference, awesome. So inference is when you use whatever you saw in your sample to make an inferred guess about the parameter. Okay, hypothesis testing is sort of backwards. Let's put an arrow like this. So in hypothesis testing, what you do is you make a guess about the parameter. And then you check it against the statistic. Okay, and that's the hypothesis test. So you can sort of think of them as like the opposite or the backwards of each other. One of them starts with the sample, then goes to the population. The other starts with a guess about the population, and then checks it against the sample. Okay. So what we're going to find out is that for each of the different parameters there are for populations, there is a different hypothesis test. So for each different type of parameter, there is a different type of hypothesis test. Okay, so these hypothesis tests are named about the type of parameter that you are making a hypothesis about. So for instance, recently, all of our null hypotheses have been something of like, oh, I think the proportion of people who watch hentai is 13%. Or I think the proportion of people who have cheated on their spouse is 13%. Or I think that the proportion of wheat, the percentage of wheat in the shipment that's bad is 13%. Okay? So because this is always about a percentage or proportion, we would call this a proportion hypothesis test. Okay, because I said for each different type of parameter, there is a different hypothesis test. So we name them by the type of parameter. We name them by the parameter that we are making a hypothesis about. There we go. Oof, sorry about that. My brain all of a sudden felt sand in the gears. I called it a parameter. A parameter. I wonder why the hell I did that. It's weird. Okay. So without knowing it, we've been doing what are called the proportion hypothesis test. And actually, there's a more specific name for this. It is called the single proportion test. Because you see how you have one proportion that you're making a guess about. So that's why it's called a single proportion test. Okay, which means what sort of proportion tests are we going to see soon? If there's a single proportion test, what other type of test are we going to end up dealing with? If we've called this one a single proportion test. Yes, exactly, a double proportion test. Okay, so in the name, there's always going to be the type of parameter. It is a proportion test. And then we're also going to talk about how many of those parameters we're making guesses about. Okay. So just so that makes sense to you, there's like there's a standard about how we do this. Okay? You're always going to say the type of parameter, in this case proportion, and how many of those parameters you're dealing with. Single proportion test, or one proportion test, or double proportion test, or what's another way to say double? Two proportion test. Eventually we'll even talk about like more than two, like how would you do if you want to do 4, or how would you do it if you want to do 5 different proportions. They're all going to be slightly different from each other the way you execute, but it's still like the same whole idea overall. Okay, so we are going to go more in depth about the one proportion or single proportion test. Okay, so I'm going to pause for a moment because I think people possibly could be writing stuff down. So I will wait just in case. Give you a moment. I guess I should ask if there are any particular questions either. Are there any questions about inference, hypothesis testing, the name, how we name them, the fact that we've been dealing with proportions, anything about what a parameter is or a statistic? Okay, cool. Awesome. Okay. So let's go forward. Okay, so we're going to talk about two different things. We're going to talk about one proportion inference, and we're also going to talk about one proportion hypothesis testing. Okay, so from now on, we're going to sort of like deal with the two of them together. So it's always going to come in pairs. We're going to talk about something, and we're going to talk about how to do the inference for it, and we're also always going to talk about how to do the hypothesis testing for it. So eventually we'll learn how to do two proportion inference and two proportion hypothesis testing. So just know that they always come together. Okay. So there's some nitty-gritty details about when is it that you can actually do the test. So there are rules or guidelines as to when it is appropriate or not to do inference or a hypothesis test. Okay, so what we're going to find out is that sometimes, just because of like the reality of the situation, like the inference you're trying to do will not be accurate, and the guidelines would say don't do this right now. There's like issues with your data, or you want to do a one proportion hypothesis test. The guidelines would tell you whether or not like it would make sense to do a hypothesis test. Okay, so there are two things you need to know. There are two requirements that need to be met to perform the inference or hypothesis test. 1. Okay. This has to do with the sample. The sample's observations are independent and are from a random sample. So I can explain what that means. I'll roll up a little. Okay, so there's two things here. The observations have to be independent, and they need to be... Oops, that's not okay. And are from a random sample. Okay, so what this is telling you is that, let's say that your data is not from a random sample. Your data, in other words, your sample information, is not random. Then performing one of these tests is a no-no. You should stop. You can't perform the test. Your results will be meaningless. These results are only valid if you got a random sample. And let me give you some examples of this. Like, what would not be a random sample? Let's say that you're interested in like figuring something out about Ohlone students, and you want to use a hypothesis test to make your decision. Let's say you show up at the library and give everybody a survey to fill out. Unfortunately, this is not a random sample. And does anyone have any guesses as to why it's not random? I know that it's the middle of the day, perhaps you're full from lunch, but like, imagine the situation. Well, yeah, so definitely they're not random. So let's talk about the ways that it's not random. Like, let's say that you just show up at the library and give everybody a survey. That sounds like it could be random, but there's some problems with it. Like, who are the people you're not going to get in your survey? Yes, thank you. People who don't go to the library are not going to be in your survey. Yeah, I know, that was sort of funny. There are very few illiterate people, so let's just be a little kinder and be like people who don't go to the library. Okay, so does it make sense? If you're doing a survey about Ohlone students, not all Ohlone students necessarily go to the library. So this would not be a very good sample to use to make your decision about Ohlone students, because your results would really only apply to the students who happen to go to the library, right? And it sort of makes sense, like, how might the people who go to the library differ from people who don't go to the library, like, practically speaking? Like, Like some people go to the library and some people don't. Like what are things that might be different about these two groups that will affect your results? Yeah. So if you can't make the time to go to the library, what else might you not be able to make the time to do? Like if we're talking... What? Yeah, right. So they might have lower grades, right? People who are too busy to go to the library might not be able to study. They might have lower grades. But your sample results would only be good for the people who do have the time to do it. So you can't draw a general conclusion, basically. So you need a random sample. Okay, so if you don't have one, stop. The more confusing part of this is them being independent. What does it mean for the observations to be independent? And the way you should think of this is that two observations... Actually, let's type this. Two observations are independent if the outcome of one does not affect the other. Yes. But not just they can happen without each other, even more generally, the outcome of one of the observations doesn't affect the outcome of some other observation. And there's actually some really cool examples of this. So let's say that you look at couples. And let's say you look at their heights. If the man is tall, what are you more likely to see about the female? If the male in the relationship is tall, what might you be more likely to see about the female? Actually, I would not quite say very short. I mean, because obviously there's a height differential between men and women. Very tall men are actually more likely to end up with what? I mean, like some people have a thing for it, like very tall men and very short women or whatever. But people who are very tall, like a very tall person is much more likely to also marry a very tall person. Likewise, how do I like taller women? Yeah, so if you have a very tall man, you're more likely to see a very tall woman. So like if you look at the man, or let's just say male and female from a couple, their heights are not independent. Because if one is tall, the other is usually also tall. If one is short, the other is usually also short. There is an effect of the height of the male on the height of the female, in the sense that people who are tall usually hook up, or people who are both short usually hook up. Obviously, there are people who like buck this trend, but in general, that's what happens. Here's another good example. What's like a card game where only one person can win? Cool, Uno. So let's say you have 4 people playing Uno. Okay. So there's person 1, person 2, person 3, and person 4. If I told you that person 1 won the game, what do you now know about the other people? They lost. In other words, these outcomes are not independent. Because if one person wins, the rest of them have to lose. That would be an example of how the outcome for one person, their winning, affected everyone else. They now lose. Okay, and it's actually really easy to like not realize this. There's like lots of stuff in real life where you think that you're getting independent results, but actually it's like sort of like a game, or there's some sort of rules or conventions where once you know the outcome from one thing, then all the others, you can say something about them. So you have to make sure that the outcome of one of your observations does not affect the outcome of the other observations. Does this sort of make sense what I mean by independent? Anything you want to ask about it? Okay, cool. Awesome. Okay, so as long as your observations are independent and from a random sample, you're good. These are not that hard to figure out. You just look to see if it says it was chosen randomly, and then you sort of look at it and you're like, yeah, that seems independent or not. It's the next requirement that's going to be the difficulty. Okay, so this is called the success-failure condition. Okay, you need at least 10 each successes and failures in the sample. Oh, sorry. You need to expect at least 10 each successes and failures in the sample. So I'll explain what I mean by this. I'll also explain what I mean by success and failure. Okay, let's go back to the hentai example. Okay, remember for the hentai example, we said like, our guess is, we'll just make this up, 13% of teenage boys watch hentai. Okay, so you're guessing that 13% of boys watch hentai. So let's say that you choose to interview 20 boys for your sample. Okay, so what percentage of these 20 boys do you expect to watch hentai, given the hypothesis that you've made? Like, remember how we always assume the null hypothesis? We've collected 20 guys for our sample. What percentage of them do we think watch hentai, given what I've written down? Yeah, exactly. So you would expect 13% of the 20 to watch hentai. Okay. These people would be called the successes because they successfully meet your criteria. You're looking for 13% of people watch hentai. Now, what percentage of them do you expect to not watch hentai? Yes. You would expect 80%, 87% of them, of the 20, of the 20 to not watch hentai. These people would be called the failures. So does it make sense? You're going to say, I think some percentage of people do this. The people who do that are called successes. The people who don't do that are called failures. It's really weird with the hentai example. The successes, they're still independent. That has nothing to do with this. Although I guess they're not really independent. If your friends watch hentai, what are you more likely to do? Just because they're your friends and you hang out with them a lot. Yeah, exactly. So that's actually why when you would do a sample like this, you would make sure that you get random people from like different schools who aren't in the same school, friend group and stuff like that. You couldn't just interview one group of friends. You would have to take a random sample from the school. That would more or less ensure that your samples are not independent or are independent. But what I'm pointing out here is that what do we mean by the success and failure? It's supposed to be that, so successes means you meet the criteria, failures mean you don't meet the criteria. So what is 13% of 20? So remember, n equals 20, your p equals 13%. So the number of successes that you expect are n times p, which is 20 times 0.13. In other words, you expect, that's 2.6. You expect 2.6 of those 20 guys to watch hentai. Likewise, you have 20 guys, the rate of failures is 0.87. So the number of failures that you expect would be n times 1 minus p, which is 20 times 0.87, which is, I'm putting the calculator, 17.4 of them. You expect 17.4 of those 20 to not watch hentai. Now, according to my guideline, how many successes and failures do I need to expect in my sample? So I expect 2.6 people to watch hentai. I expect 17.4 of them to not watch hentai. And I need at least 10. So this is no go. There need to be at least 10 successes and 10 failures. But given my sample size of 20, I can't use... but given the sample size of 20, I only expect 2.6 successes. What this is telling me is that I could not use a sample of 20 to perform the hypothesis test. Okay, so this guideline is telling you, hey, I know that you were hoping to just take a sample of 20 people and then perform your hypothesis test, but this is not going to work out. You did not meet the success-failure condition. You need at least 10 expected successes. So I'm going to pause for a moment. And see if this makes sense. Everyone tired today? So. How are y'all feeling? Real talk. Always tired. No, I get that. I'm sleepy too. Yeah, food coma. The food coma is real. I ate just before this. I feel it. Okay. This is what I'm gonna say. I want you to dig a little deep and think about this. And we're gonna call it quits after this, because I could just tell everyone's tired, and I don't want to have you just fall asleep on me. So my question is, we have these 20 people. What you're gonna do is you're gonna take the proportion from the null hypothesis, and you're gonna use that to figure out how many of those 20 you expect to be successes. So you just do the 13% times the 20 and you get 2.6. Does it make sense that that's too small? You needed that number to be at least 10 to get the green light to say, oh, 20 people is a fine number to do your hypothesis test with. The problem here is that you're not getting a big enough number. If that number was 10 or bigger, you'd be able to say, oh, okay, yeah, I'm cool. 20 people is enough. But it wasn't. Yes, exactly. So let's just write that down. So like an example where it would go well is you'd say, hey, let's make n equals 200. So then you would say, well, the expected number of successes would be your n times your p. My n is, actually my bad, yeah, let's just make it 100. I don't need 200. You would say I have 100 times 0.13. 13% of 100 is 13 successes. And you'd be like, oh, we're good. 13 is more than 10. And then you would do the same thing for the number of failures. So the number of failures is going to be n times 1 minus p. Your n is 100. 1 minus 0.13. Which is going to be 100 times 1 minus 0.13 is 0.87. What's 87% of 100? We expect 87 failures. Is 87 bigger than 10? Yes. Both of those numbers are bigger than 10. It'd be like, you're good to go now. You can do a hypothesis test. Your sample size was big enough. So the lesson to be learned here is if the expected number of successes / failures is not larger than 10, then your sample is too small. And there's a formula for doing this. Your formula is n times p for the number of successes. Your formula is n times 1 minus p for the number of failures. Yeah, the number of expected has to be 10, so the number you get from those two formulas has to be bigger than 10, always, yes. At a minimum, you need 10. If you go under 10, it's no good. Okay. Mucho bueno? Making sense or no? Hopefully. Is it sort of making more sense? This is going to take a second. Yeah. Okay, so the way you're thinking about this is what you're focusing on is whether your sample is big enough. Very good question. It is because... Let me think of how I'm going to explain this. So there's a lot of complicated math you can do. And what you find out is that if these numbers are not bigger than 10, then the type of distribution you're going to use to do your calculations is not going to be normal. So you remember how when we do this, the confidence interval is the point estimate plus or minus 2 times the standard error. Does everyone remember that formula? We've been using it for quite a while. Point estimate plus 2 times the standard error. Yeah. Where does that 2 come from? Or what does that 2 tell you? I guess there's 2 questions there. The 2 comes from where, and what does the 2 tell you about the confidence interval? Yeah, it tells you that you're dealing with a 95% confidence interval. And then where did we get the 2 from to say, oh, that's actually going to be 95%? I know it was a while ago, but... like, where did that 95% get connected to the 2? There's a thing we learned, what feels like forever ago now. Yes, the empirical rule. Thank you. And in what distribution were we learning about that the empirical rule applies? There's a particular type of distribution for which the empirical rule applies. Yes. And it just so happens that if your number of successes or number of failures was less than 10, we could not guarantee that you're actually working with a normal distribution. Like something weird happens, basically. You get this other thing. But as long as that is bigger than 10, there's like this complicated math that can show that, then you know that you're dealing with a normal distribution. So that like sort of answers your question. But like part of it I like just sort of hand waved away by saying like there's this stuff that people know. If you're less than 10, then maybe you might not have a normal distribution, which would mean that you couldn't use the empirical rule, which means that you couldn't do your confidence interval, which means you can't do your inference. So there's like a long string of things there. Okay. Yeah? Feeling, is it making a little more sense about like, you need the 10 there so that all of this works? Because it all comes back to, I'm trying to do inference. That means I'm going to make a confidence interval. Well, that means I have to be able to use the empirical rule to get that 2 there. That means I have to be dealing with a normal distribution. That only happens if you're bigger than 10. Okay, but I want to know also, does it make sense how I calculated how many successes and failures that I was expecting? You have the n times p and n times 1 minus p formulas right here. I guess I should write down, where does the p come from? P comes from your null hypothesis, and then the n is the sample size. Or you could use p hat from your sample if you're doing a confidence interval. Either way, the p is going to come from your sample or your null hypothesis. Well, there is no 1, but there is a 1 minus p. P is the probability of success, and so the failure is the remainder. So if you have like 13%, the remaining amount is like 100% minus 13%, and that's the same as 1 minus p. So that's why you have to do n times p and n times 1 minus p, because you need both the number of successes and the number of failures to be bigger than 10. And then the probability of failure is the leftover from the probability of success. The probability of success is 13%. Probability of failure is going to be the 87%. How do you get that? 100% minus 13%. That's the 1 minus p. Sort of making it. Talking about this formula here. Just want to know if like people feel comfortable like where to get the numbers from now. Yeah, the 1 is the equivalent of the 100. The p is the equivalent of the 13%. So the 1 minus p tells you the probability of failure, the leftover from the 13%. But yeah, 1, yeah, that's exactly yes. Exactly, 1 meaning the whole, yes. 1 minus p gives you the remainder from p. If you take your 100% and subtract the 13% out, you get the leftover for the failures. Nice. Anything else people want to ask? Looks like it's making more sense. Tomorrow we're going to come back. We're going to like do a whole example given that we know. Well, actually what we're going to do is learn what needs to be true for the hypothesis testing over proportion. So we'll do that. Okay. Oh yes, we need to talk about that. It was supposed to be this week, but real talk. Let's do it. What's it called? Yeah, I know exactly. Let's ask about how you feel about the exam. I'm gonna put a poll. How do you feel about an exam? Your options are gonna be: I would die. I would not be happy. I wouldn't care. I would be fine. And yeah, we're gonna see. And I would be great. So let's save this. And let's look at the results. So vote. If we invested in Bitcoin. Oh man, Elias is always with the, or Elias, I'm not sure how I'm supposed to say it, is always with the Bitcoin for sure. So yeah, let's look at what people say. Okay, so I mean, 23 out of 20 people. Well, okay, well let me stop the recording.